Welcome. Today's notes worksheet is entitled Factoring Patterns. And so we'll be taking a look today at a variety of different patterns to break down these polynomials into a product of its factors. And factoring is definitely one of those important skill sets that we're going to be looking at all semester long. So let's see if you remember some of these patterns from previous courses, and then probably add a little piece towards the end there that'll be new. So let's go for it. Let's dive right in. It looks like the first pattern that we're going to be taking a look at is what's called the greatest common monomial factor. And I guess in this blank right here, what I'm thinking you should write in is, and this is just the way I think of it, when we talk about the greatest common monomial factor, it's really the reverse of the distributive property. So if you remember, the distributive property is really multiplying a term inside parentheses. In this case, it's really creating the parentheses and the term that'll go outside. And that term that goes outside the parentheses will be the greatest common factor. So notice what it says on your paper, by the way. I kind of tried to emphasize this as best as possible. Always look for this pattern first. So it's bolded, it's capped, there's an exclamation point. Always, whenever you're looking to break a polynomial on down, what you want to do is look to see if you can pull out a greatest common factor. So let's start it out here. I think the best course of action with these examples is for me to just do one and kind of talk you through it, and then have you maybe pause the video and try a couple on your own and come back and see if you got them correct. So let's try example one. As it says, factor each polynomial. And what that basically means is we're going to write this difference of two terms right here. This is a polynomial, a cubic as a matter of fact. And what we're going to do is change this from a difference of two terms into a product of its factors. And so we're just manipulating the expression. We are rewriting the expression. And so in this case, what you want to do, and I do this sometimes, I lightly circle the two terms. So I have the 4x cubed and I have the 6x, separated by that minus right there. And what I'm looking for in terms of the greatest common factor is something that divides evenly into both of those terms. So numerically, what divides evenly into 4 and 6? Well, 2 will divide evenly into 4 and 6. In terms of the variables, what divides evenly into x cubed and what divides evenly into x? And it looks like that greatest common factor would be x. So what we get is this monomial right here, this 2x that will come out. Once I know that that's the greatest common factor, then I need to see what factors are left over after I've pulled this out. And so there are a variety of ways to look at this. For right now, we just kind of think about 2 times what would give us the 4, and probably get that right there. And x times what would give us the x cubed, and I'm hoping you would see that that's an x squared right there. Minus goes in between, and then same thing here, 2 times what would give me the 6, and we get the 3 right there. And I already took out the x, so there's no variable on the back. And so that's basically what it would look like. We're going to do some harder ones at the end of this notes worksheet, and we might look at this from a slightly different perspective, but basically this is the premise. Greatest common factor comes out nicely. So I guess what I'd encourage you to do is pause the video for a moment and try letters B and C. When I come back, I'll probably do them in a slightly quicker fashion. Okay, well, let's see how you did. So when I looked at these two right here, I pulled out a 9x to the 4th. So x to the 4th is what goes into this, and it's what goes into this. And so we've got that piece, and it looks like 9 times 3 would give me the 27. X to the 4th times x would give me x to the 5th. And then I have what looks like a plus 2 on the back end there, and that's pretty much it. 9 times 4 factors of x. If we really wanted to think about this, this is 9 times x times x times x times x times the 3x plus 2. Wonderful. Now this one's a good one here. We're going to catch this on the back side, something that'll look very similar to this. But for right now, I have 2 terms really separated by that plus. So this and then this. And what I would do is think about what term is in both of those values. So in this case, it looks like I have an x plus 3 that is common to this part of the polynomial and this part of the polynomial. So I believe x plus 3 is what comes out. So it's a little different. It's not a monomial that's coming out. It has 2 terms, so it's what's called a binomial, but it is still the greatest common factor. And then when I pull out an x plus 3 from here, so this is now gone. I hope everyone sees we're just left with x squared. Here's my plus in the middle, goes right down there. And then I look at my second term, everybody, pulled out the x plus 3, and so the only thing that's left is 5. A good way to check your answers is to just redistribute or just kind of multiply it back in, and if you did, would you get the original? Yeah, absolutely. That looks good. Okay, good. So as I said, always the first thing you're going to do when you're going to factor is to look for the greatest common monomial, or the greatest common factor, basically. Okay, let's go get number 2. These are the easy quadratic trinomials. Quadratic means it's a polynomial degree 2. Trinomial means it's 3 terms, 1, 2, 3. And so, I don't know, this is the way I kind of phrase it here. It's sort of the reverse of foiling, so I'm just going to write anti-foil. So you remember, of course, first outside, inside, last. This would be the exact reverse of that operation right there. And this is what I'm just going to write here. These are, again, relatively easy once we get the hang of it. But what you're going to do when all is said and done is look for 2 numbers that multiply to C, and so the C value is the back end there, that constant on the back, and add to B. So that's the pair that we're going to be looking at. So 2 numbers that multiply to C and add to B. So here's your C, here's your B. If you kind of figure out that combination, most of these are going to be pretty easy. So same premise, I would encourage us to do example 2 where I'm going to go ahead and anti-foil it, meaning create 2 binomials. And again, this is factoring because it's a product of these 2. There's multiplication right in between. And what we want to do is, as I said, reverse foil. So I look at the first, and I had to get x squared. That'll come, of course, from x and x. And then this is where I wrote in that blank, I'm looking for 2 numbers that multiply to 8 and add to 6. And so I'm hoping everybody would realize that would be a positive 4 and a positive 2. And that's what would go on the back end. And now, of course, if I foiled first, outside, inside, and last, should get this right up here. Good? All right, everyone. Be great if you can do B and C. Pause that video for a second and come on back, see how you did. All righty. Well, when I did this, I first made my 2 binomial parentheses. I knew, obviously, x and x to multiply to x squared. Sorry about that. Something popped up there. But anyway, x and x give us our x squared. And then I'm looking for 2 numbers that multiply to negative 18 and add to 3. And I got a plus 6 and a minus 3 there. Nice. I did the same thing over here, of course. Got my 2 parentheses taken care of, x and x. And now this one, just be careful on, 2 numbers that multiply to positive 40 and combine to negative 13. So must be negative and a negative here. So minus 8 and minus 5 would do it. All right, and those should be pretty straightforward. Just being able to sort of anti-foil that piece. We're going to get into some of the harder ones on the next pattern. All right, so let's go for it. Number 3, of course, is the same exact thing. It's a quadratic trinomial. The only difference, of course, is now I'm going to throw a number in front of the x squared. So that's the key. The premise is definitely the same. So everyone, if you would, for number 3, can you go ahead and put in the fact that we're going to reverse foil or anti-foil this? And I have a couple ways to kind of pull this off, and you take it for what it's worth, of course. But one way to think about it is if you have really good number sense, probably the most efficient way to do it is just with a little trial and error. Probably we'll be able to figure out most of them relatively fast. Apparently I don't know much about humility here because, yeah, I have a great method. I probably know about 3 or 4 decent methods to factor that, you know, if you follow it, you can pretty much get it every time. So I'm going to show you my favorite one. I think it's really good, and foolproof is close to being the truth there. It really, if you can follow it piece by piece, it always works. So I'll show you that method, and as I said, if you like it, great. If you don't, use something that you've seen in previous courses. So let me do letter A just with a little trial and error, just to kind of get us thinking about it, because as I said, this is the way I would do it. Just good number sense, really, you've probably pulled a lot of these off. So what you're doing is reverse foiling. So the first order of business is to realize I have to get my first terms to multiply together to get 2x squared. And so that one's pretty straightforward. You know it has to be a 2x and an x. That's what's going to multiply to 2x squared. Now the back part is the intriguing part, because now I have to get two numbers that multiply to -6 and then get the outside and inside combined to -1x. So what you would do maybe is just kind of think of some numbers that multiply to -6 and then go for it. So you might do something like, 1 and 6, just to try it out there. So you would maybe do like a 1 and 6 and hope for the best. And you know they would have to multiply to a negative, so maybe you do a plus and a minus or something like that. But regardless, you would have to combine the outside and inside to get a -1x. And as I look at my combination, I get a 12x and a 1x. Well, there's no way to combine a 12x and a 1x to get -1x right here. So this is just, it's the wrong combination. So what I would do is come back over and erase and pretty much start again. And so you might try a different combination. You know it's 2x and x, maybe something like this. Now I'm going to go with a 3 and a 2, and I'm going to see what happens. Oh, outside is 4x, inside is 3x. I can work with that. I can get that to go in there. And if I do a minus here for a -4x and a plus here for a +3x, I think I have it. And so that's just trial and error. Just you're foiling this out to make sure it's equal to that. Okay, great. That's going to be our answer. I'm going to erase that just for a moment so I can show you my method. And again, please, I'm not trying to reinvent the wheel here by any means. If you know how to factor really well and you can do these nicely, there's no need to reinvent the wheel. So here's my method in a nutshell. So basically, don't like that number out in front. It's not easy to work with. So what I'm going to do is actually move it and combine it with the back side. So what I'm going to do is actually take that 2 and I'm going to bring it over to the back, and 2 times 6 is 12. Now this is something that can be factored pretty easily. So what I do is I create my 2 parentheses. Now that it doesn't have a number in front of the x squared, and by the way, leave a little room in front if you would, I know it's going to be a little x and x right there. Now all I have to do is think of 2 numbers that multiply to this and add to this, and I'm thinking it's a -4 and a +3. Now here's the problem. Obviously, everyone, this is not the original up here. I need to get a 2x squared out in front. The only problem is I don't know where that 2 goes. I don't know if it goes here or here. So what I'm going to do, everybody, is put them in both. I'm going to do it wrong for just a moment. I'm going to overcompensate and then fix it, and then whatever comes out should be the answer. So I put the a value back in both because I don't know where it goes. But now what I need to do is sort of figure out where's the extra 2. And I put an extra 2 in somewhere. And if you notice, 2x minus 4, everybody, isn't there an extra factor of 2 in here? So I'm going to divide it out. There was the extra 2. And when I factor that out, I get x minus 2. This and this gives me that. Nothing extra here, right? So this is just 2x plus 3. And there it is. Works great. I'll do it one more time and then maybe ask you to do B and C. We'll see how we're doing on it. So here's my method in a nutshell. I take my 2 and move it over to the other side, just temporarily. So plus 9x, and then 2 times 9 is 18. What I'm looking for now is 2 numbers that multiply to 18 and add to 9. That's not too bad. I can pull that off. And so I'm going to go ahead and do x and x. It looks like a plus 6 and a plus 3. Okay, very nice. Now again, I have to put the 2 in because these have to multiply to 2x squared. Unfortunately, I don't know where that 2 goes, so I put it in both. And then I realize, okay, I put it in both. I overcompensated. Somewhere there's an extra 2. There it is. There's the extra 2, so I divide that by 2, and then I get x plus 3 and 2x plus 3. And there you go. That's how it works. it would be great if you could try C and D by yourself anyway. Again, you do not have to use my great method here. Use whatever method you see fit and see if you can come up with something worthy. All right, I'm going to run through my method a little faster now. So let's see, that goes on over. Get that right there. I can factor this. I believe it's going to be x minus 6 and x minus 5. Now the 15 goes back in, both of them, because I have to get this and this to multiply to 15x squared. The problem is I don't know where that 15 was supposed to go. And in this case, if you look at the extra, I seem to have an extra factor of 3 in here. So when I do that, divide by 3, I get 5x minus 2. And here it looks like I have an extra factor of 5. So remember when I said there's an extra factor of 15 in this one that I put somewhere in here and here? Well, part of it was here, and the other part of it was here. 3 times 5 is 15. So it might come up in one, or it might be a combination of the two. But regardless, it's factored. 5x minus 2 times 3x minus 1. And remember, everybody, there's only one way to figure out. If you got it right, FOIL that out. If you get that original, you got it. One more time. 10 goes over. I can factor this. I'm thinking, how about an x minus 15? And how about an x minus 2? The 10 goes back in. Beautiful. And somewhere I put an extra 10 in. It looks like part of it was here because coming out is 5. And so I get a 2x minus 3 from here. And then it looks like there's an extra 2 in that binomial. And so there's your extra 10, 5 and 2. And it looks like I get 5x minus 1. That looks great. So hopefully that was enough just to kind of see it. As I said, if you know how to factor these, great, great, great. All right, let's move on to example 4. And I guess here's what I'm going to do. I'm going to just do the first one really fast. I think we can gloss over this a little bit and just fill in what we need to. But just wanted to show you one thing. It says, what do these quadratic trinomials have in common? And what they have in common is how they factor. If I was to ask you to factor this, you would factor it as x plus 3 times x plus 3. I think you could pretty much all pull that off without too much difficulty. If you notice in this case, it is a product of two factors, and as it turns out, it's the same factor. So what we can do is rewrite this as, instead of x plus 3 times x plus 3, well, anything times itself, of course, is just being squared. So that would be x plus 3 squared. Okay, letter B. Let's just do this quick verbally and just write in what we need to. If I asked you to factor this, guys, you would say it's 3x minus 1 times 3x minus 1. Better written as 3x minus 1 squared. So a product of two factors that happen to be identical. And then the last one here, letter C, if I asked you to factor this, this would be just x plus 1 times x plus 1, or x plus 1 squared. So there are just a couple names that go with these, and we will see a lot of this in the future, being able to factor this and make it look like this. This form is going to be key for a lot of little algebraic concepts that we're going to see this semester. Anyway, it says each of these polynomials is called, so the original problem there is what's called a perfect square trinomial. And we don't have to go into all the little algebraic reasons why that is. You can see, though, perfect squares out in the front and on the back, perfect square in the front, perfect square in the back, and then the middle term also has some format to it that makes it a perfect square trinomial. But regardless, that's okay. I'm going to shorthand this if you don't mind. Every perfect square trinomial factors into what is called the square of a binomial. You'll hear me actually use that phrase a lot over the course of the semester, as again, we will be doing exactly this piece. So that's a nice thing to have when it's in the square of a binomial. Keep that in mind if you get an opportunity. All right, let's move to the next board then. Next pattern that comes up is what's called a difference of two squares. I think you've seen this before. And so here's what I have. Difference of two squares. Difference means subtraction. Two perfect squares. And this comes up a little more than you think. It actually looks pretty obscure, but it's a little more common than you would think. And so in this case, it sums to what is it factors to what is called the sum and difference pattern. So it breaks into the two linear parts there, 1 plus, 1 minus. So you can kind of write that here if you want, sum and difference pattern. Something like that. Again, not mandatory. I think what I'll have us do is I'll do letter A, of course, with you. Maybe have you pause and do B, and then maybe C also. C is a hard one. Okay, so the first thing, obviously, with a lot of factoring is recognizing a particular pattern, and then the second piece is to apply that pattern. So I look at this, and I see a difference of two perfect squares here and here, and so what that immediately tells me is that's the pattern we're focused in on here, and it factors in a very particular way. So all I have to do is think about what times itself will give me that square out in front. So x and x. What times itself will give me that perfect square on the back, 8 and 8, and one's a plus and one's a minus. And that's it. If I was to FOIL this out, these two binomials, I should get this piece right up here. All right. Would love for you to pause. Try B. B I think is manageable. C is a good hard one. Try C also. Okay, here we go. Well, when I did this, I did recognize that it is a difference of two squares. And so 5x times 5x would give me that piece. 6 and 6 would give me the back. And if I make it plus and minus, you could see that the outside and inside would combine to 0. And so I wouldn't get a middle term. And that's why that works out if you FOIL it. Now this one, as a matter of fact, takes two steps. It is a difference of two perfect squares. X to the fourth actually is a perfect square, and so is 16. So my first order of business is to just treat it as a difference of two squares, and what times itself would give me x to the fourth? X squared and x squared. What times itself will give me 16? 4 and 4. Plus in one, minus in the other. And that's looking great. Now you're always, with factoring, you're always looking to break it down further. So this is an interesting piece right here. This actually can't be factored. In fact, we'll kind of write this up in just a moment or two. But this is what's called a sum of two squares. Can't touch it actually. But this, if you notice, actually can factor further. This by itself is a difference of two squares. And so what we would do is keep this as a prime quadratic factor, and then factor this one as x plus 2 and x minus 2. So you have that as your overall answer. A quadratic factor times a linear factor times a linear factor gives me this quartic up here. So I don't know where you maybe want to put this. I'm going to just put it off to the side if I get an opportunity here and it fits. But just know there is what's called a difference of two squares, but there is no sum of two squares pattern. So something like it is prime. That's not a bad idea. Again, put it wherever you'd like, but that's why we couldn't touch this one right here. And I will definitely put it on some of the practice problems and some of the assessments that you'll see. See if you'll take the bait, but try not to. Sum of two squares is prime. Okay, now we start getting into some of the harder ones. So let's take care of this next one, number 5 on your paper. And it's what's called the sum or difference. So now, guys, there is a sum and there's a difference pattern for cubes. So we just worked on the squares. Now we're going to go cubes. So everyone take a peek at what I have just algebraically here. This one, I guess the bottom one, would be a sum of two perfect cubes. There they are. This one would be a difference of two perfect cubes. And what we could do is rewrite this expression into a product of factors. In this case, as you can see, there's a linear factor times, here's a times right in between, of course, a quadratic factor. So linear times quadratic. And that should be great. I'm going to kind of show you how this plays out here. I wouldn't memorize this. I don't really memorize this piece. I'll try to show you a trick or two to make it work. Okay, so the first order is to recognize. And so the first thing I see here is a difference. This obviously is a perfect cube, and 8 happens to be a perfect cube. Think about what cubed would give you 8. So the way to pull this off, everybody, is to make a small parenthesis times a larger parenthesis. And the way you kind of do this, to start it out, is this is your linear factor right here. So for the most part, this is going to be pretty straightforward, because all you're going to ask yourself is, what cubed would give me this? Well, obviously x. What cubed will give me that? Obviously 2. And if that's a minus, this is a minus. And so the linear part to this is x minus 2 from here. All right, now here's the idea. We have 3 parts of the quadratic to fill in. And I'm going to go from easiest to hardest. So it's 1, and then 2, and then 3. So basically, I'm going to start with the one in the front. And I would just ask myself this. Factoring and multiplication go hand in hand. So when you think about this, x times something has to give you x cubed. So x times what would give us x cubed? Well, it has to be x squared. X times x squared is x cubed. Hope everybody realizes that. By the same token, on the back side is where I'm going to get this piece. So ask yourself, -2 times what would give you -8? Well, again, just good number sense here. -2 times +4 will give you -8. So those are the parts that when you multiply it back out would give you this polynomial right here. Now the key to the whole thing is the middle term. And the middle term is what's going to get rid of all the other things when you multiply. Make sure everything else cancels out. You'll get x cubed from this. You'll get -8 from this. Everything else would have to go and cancel when you multiply. So here's how it works. Here's the little trick. I go back to my first parentheses, and what I do is take those 2 terms and multiply them together. So it's x times 2, which is 2x. And in order for everything to cancel out, basically it's the opposite of this term right here. So if that's a minus in here, then this is a plus. And you would see, if I asked you to do this hefty polynomial multiplication and you were to multiply everything, everything would cancel except the x cubed and the -8. By the way, this is always going to be prime. This quadratic right here can't be factored. So I'm just going to write prime on that. You don't have to if you don't want to, but that quadratic will be prime. Okay. It would be great for you to maybe try B and try C and then just see how you did. I'll do B and C probably a little quicker than I did letter A. Well, let's see how you did if you tried it. So this is what is called a sum of 2 perfect cubes. This obviously, and 4 cubed, by the way, would give you 64. So you know right away that this has to be x plus 4. There's the linear part of this, for lack of a better description. And then I just walk myself through. X times what would give me x cubed? Has to be x squared. 4 times what would give me 64? Has to be 16, and positive, right? Positive times positive gives me positive. Good. And then very simply, again, the linchpin is the middle term there. I take these 2 things and I multiply them together and I get a 4x. And if that's a plus, in order to cancel everything out, that's got to be minus. Looks good. We'll see some of these cubes potentially over the course of the semester there. I like kind of the pattern works out really well. Let's go with letter C. So in this case, that is a perfect cube, and 1 is a perfect cube. Don't forget that one. It's a perfect square, it's a perfect cube, etc., etc. So what cubes would give me this right here? Yikes. Well, 2 cubed gives me 8, and x cubed would give me x cubed. So I'm getting a 2x and a +1 right there. That seems to be the linear part to that piece. And now let's see if I can fill in the 3 pieces over on the quadratic. 2x times 4x squared would give me this. 1 times 1 would give me that. And then everyone, just multiply those two things together. 2x times 1 is 2x. If that's a plus, that's a minus. So you get 4x squared minus 2x plus 1 on that quadratic times this linear. Linear times quadratic gives you the cubic. All right, very nice. Let's go on to the next. So next one is going to be grouping. And just maybe we'll write a few things in and then try another set here, see how you're doing with all these. So here's what I have with grouping. I grouped the first two terms together. And the last two terms together. So write that in there for me. Two terms together, all right? And then this is going to be a little vague, but you'll see it in action momentarily. And then very simply, then treat it as a greatest common factor. That's what GCF will be, as a greatest common factor problem. All right, so I'll show you what that means, but just jotting that down, even though it might not have a lot of context at this point, hopefully it'll click momentarily. So let's do our A, B, C, and then D is a great tough problem there, but we'll see what happens when we get to it. So when we talk about grouping, there is a reason that it is called grouping, because we're going to use grouping symbols. And obviously the most common grouping symbols to use would be parentheses. So what you're going to do is use parentheses around the first two terms. I like personally doing this. I like putting parentheses around the second two like that with the plus inside. Some don't, and if you've learned it this way, or if you've learned it in a slightly different manner, that's fine. Doesn't matter. But I kind of like doing it that way. So what I do now is treat this as all greatest common factor. Look at these two right here, everybody, and I guess I would ask you, what is the greatest common factor to those two terms? It looks like x squared. So what I'm going to do is pull out the x squared, and if I pull out x squared, I get the x minus 4. Good. Then I come over here, the second two terms, and what is the greatest common factor of these two? And it looks like a positive 2. Here's where I include the plus symbol. So if it's a positive 2, make sure you put a plus out in front. That is the key. Just be careful on that. And notice what happens when you pull out the 2. You get that same x minus 4. And that's how you'll know if it can be grouped. If you get this piece right here that are the same, then you know it's going to be done by grouping. If not, then I'm afraid it just can't be grouped. Now, if you notice at this stage, it should look familiar. I have two terms, this one and this one, separated by that plus that I had you put in. And if you kind of look at this piece, now I'm still going to go greatest common factor. And as a matter of fact, it looks very similar to where we started this lesson. X minus 4 is in both of these terms. It's in this one and it's in this one. So I pull out the x minus 4. And when I pull out an x minus 4 from here, this goes away, and I have an x squared left. Here's my plus, everybody. And when I look at this term right here, I pull out the x minus 4, it goes away, and I get a 2. And that works nice. You always look to go further, but it doesn't look like those break down. Well, let's do B. Going to come on over here and do parentheses around each. Same premise. Factor by greatest common factor on those two terms. I get a 3x plus 4. Now here, just anytime I see a minus there, I automatically pull out a negative with this. Just that's the way I do it. And just so to make sure it matches up. So I would pull out a minus 2 here. And notice if you pull out a minus 2 from here, you're going to get a positive 3x. And if you pull out a minus 2 from here, you're going to get a positive 4. I hope everybody sees that. There's your negative 6x. There's your negative 8. When you pull out that negative 2, these become positive. Okay, and now if you notice, 3x plus 4, 3x plus 4, we're in business. So two terms, 1, 2, separated by this minus right here. And of course, 3x plus 4 is common to both of those terms. So it is a greatest common factor. It comes out. When it comes out of this piece, the left-hand side, I get x squared. And when it comes out of this piece, I got my minus, and I have my 2. Great. We'd love for you to try C and D on your own before we wrap this on up and do our last pattern of the lesson. All right, let's see how you did. Pull out my x squared. I'm sorry, 3x squared, my fault there. So pull out 3x squared, and looks like I get x minus 1. Now here's where you do want to be a little careful. Oh, actually, no, it doesn't matter here. Pull out the plus 2, and you still get the x minus 1. I was thinking of something slightly different. That'll happen on the next problem. And as you can see then, x minus 1 is common to both. Let's pull it out. X minus 1 comes out. Here I get 3x squared from the left, my plus right smack in the middle, and a positive 2 left on the right-hand side. Looks good. Always just do a quick check. Does anything break down further? In this case, no. All right, now letter D is the killer, but it does factor by grouping. So let's start that out. What's the greatest common factor of these two terms? Everybody, it is definitely x cubed, and I get x minus 1 as a result. Now here's where you do want to be a little careful. I wish this came up maybe on A or B or C, but at least it's coming up. In this case, it looks like, hey, wait a minute, there's no greatest common factor here. Well, what I would do then is think of it as a greatest common factor of positive 1. So I would actually pull out, and it really is there even though it's not written, I would write it out. So it's 1 times x minus 1. That I think is the key, is to actually show the greatest common factor of 1. And now it looks like all the others. So hopefully that makes sense, pulling out that 1. Now everyone look, I have this right here and this right here. What is common to both of those terms? It looks like x minus 1 is in the left and x minus 1 is in the right. So I pull it out, and I get that right there. Okay, now, if you stopped right here, perfectly fine, no big deal, but you can go further. Wondering if you recognize anything. This is fine as it is. It's just a linear factor. This, everybody, is exactly what we did up above, a sum of 2 perfect cubes. And as a result, it factors exactly like what you saw above. It factors into another linear times that big quadratic. So I'm not sure if you recognized it, but that is the key to factoring. I always say it's 2 elements. It's recognizing the pattern and then applying the pattern. And if I do exactly what I did up above with a sum of 2 cubes, I think you end up getting x squared. How about a minus x and a plus 1? That, I think, would be the ideal. All right. Some good stuff. All right, now, guys, we get into the last piece, and it gets slightly harder. So refocus if you need, and let's do kind of our last part right here, and this will segue into the next notes worksheet as well. We'll pick up on this piece. So, if you would, factoring involving fractional and negative exponents. Here's what I'm going to write in. It's going to be greatest common factor. So if you would, just let's do this, greatest common factor. And let's see. Yeah, let's do this. Just right next to it, if you would, just write the lowest power. And I'll tell you what I mean by that as we go through. So greatest common factor will always be the lowest power with these. And they're going to get a little ugly on these exponents. That's the trick. So what I'm going to try to do is a quick investigation to show you what this would look like with just good basic numbers. So when we get a little heavier, hopefully we can segue nicely into that. Okay, so let's read what it says and then go for it on this last piece. It says, after we factor out a GCF from an expression, what calculation can be used to determine the terms inside the parentheses? Use the example to answer this question. So, okay, first order of business, guys, is let's go greatest common factor on this. This is how you would write this as a product of its factors. I'm hoping you would all agree that you'd pull out 6x squared. And notice in terms of the powers, x to the 5th and x squared, the greatest common factor, of course, is always the lower of the two. Now the question, of course, is how do I figure out what goes here and what goes here? I have to fill in those two blanks. So we did it before where we said, okay, well, I know this times this has to give me this piece up here. Well, another way to look at that then is the fact that multiplication and division go hand in hand. So if this times this gives me this, then the original, this, divided by the greatest common factor should give me what goes here. Hope everybody agrees on that. Because 12 divided by 6 is 2. And x to the 5th divided by x squared, hey, wait a minute, that's something we did yesterday. We divide powers with the same base by subtracting exponents. 5 minus 2 is 3, so keep the base, subtract the exponents. And so I hope that makes sense. I think you've seen that before. This times this is that, so this divided by this is what gives me this. And then I hope you realize that when we do the same thing over here, the original divided by the greatest common factor, we get that. So here's what I'm going to write. Take the original term and divide it by the greatest common factor. Put that in. I think you're going to need it. As the exponents get harder, I think that'll be imperative. So let's check this out. Just we'll wrap it up on A and B, and as I said, we will pick this up on the next notes worksheet. So if it's not firing on all cylinders for you, that's okay. We will get it on the next one. So everybody, letter A, two terms separated by a minus. What I would like to do is manipulate this expression and write it as a product of factors. So if we have two powers in the same base, the greatest common factor is very simply the lower of the two powers. So obviously x to the 1/2 is lower than x to the 3/2. So that's what comes out. And then if you're not sure, and that's the idea, if you're not sure, this times something needs to give me x to the 3/2. Or, and this I'm just going to work off to the side here, what we said is we take the original and divide by what we pulled out. That will give me what goes in the blank. And so, in this case, this is something we did on the previous lesson. Divide powers with the same base, we keep the base, and we subtract the exponents. 3 over 2 minus 1 over 2 is 2 over 2, which of course is x to the first, which of course is just x. Hopefully that all makes sense there. So this divided by this, as a matter of fact, is x. Wonderful. Minus goes in between, and I repeat, I don't know what goes here. Well, maybe you do. But if I don't know what goes here, well, I take the original and divide by what I pulled out. So I would do this, and if I was very formal about it, I would say I'm dividing two powers with the same base. I keep the base, and I subtract the exponents. 1/2 minus 1/2 is 0. Oh, and anything to the 0, of course, is 1. And we knew this to be the case. Anything divided by itself is 1. Or this times 1 will give it to me. I mean, just there's so many ways to look at it. But basically, that's it. There it is. Fractional exponents. Wait till the negatives come into play. Okay, last one, everyone. Regroup, refocus. I'll do the same. Two terms separated by that plus. Let's write this as a product of factors. Let's start out nice and easy with the greatest common factor. I'm hoping you all agree. 4 is the greatest common factor to 4 and 8. Now, in terms of this is hard, but in terms of this, what is the greatest common factor of those two powers? Well, the good news is, everybody, it is always just the lower of the two. And so the fact is, x to the negative 2/3 is lower than x to the 1/3. So that's what I pull out. Just like, again, let's keep it simple. X squared was lower than x to the 5th. That was the greatest common factor. Okay, so nice. I've got that. Now let's see. I have blanks to fill in. So something's going to go here. Something's going to go here. If I don't know, then I just do a little division off to the side. So everyone, you take the original, what you started with, and you divide by what you pulled out. 4 divided by 4 is 1. this divided by this. Again, I'll just kind of do this right here. I know it's kind of silly. Keep the base, subtract the exponents, you get that. So I hope you all realize that's 1. And obviously, guys, this times 1 is itself. Okay, now, plus goes in the middle. Last one, everybody. Here it is. Let's see if we can pull it off. Take the original. Again, only if you're unsure. If you just don't know what goes here, this is the formal way to pull it off. So take the original, divide by what you pulled out. 8 divided by 4 is 2. This power of x divided by that power of x, I keep the base, and I subtract the exponents. Careful with your signs, everyone. 1/3 minus negative 2/3 is actually 3/3. And sorry, I'm going to have to come down below here, which means that's 2, and 3 over 3, of course, is just 1. So that's 2x to the first, or really, obviously, x to the first is just x. And that's looking great. If you get this far, it's awesome. You really are on track. I would argue we could probably go one step further. Notice what it said in example 8. Write your answers with positive exponents. And so in this case, what we're going to go ahead and do is take the one term with a negative exponent, and we are going to move it. So in reality, the ideal expression looks like this. All right. Good. Again, we will pick this up on the next notes worksheet. So if it's not clicking at this point, don't stress about it. Get a little practice, ask a few questions, and be happy to help. This was obviously a long one because there are so many patterns to factoring. I appreciate your time and patience with it, of course. And please don't hesitate with any questions. And thank you for listening.